Very good. It's really an honor to be the inaugural speaker of the premier program. Let me start with some general statements or disclaimers. I know that from being at the meetings of Premier, I know that there's a good bit of focus on both science and technology and bringing science to technology. But by training and by my inclination, I'm more of a scientist than a technologist. So a lot of what I'm going to talk about is multi-phase flow science. But at the same time, my interest is to work with people who are really translating these into products and processes, etc. So please feel free to stop me. The format is such that you may not be able to stop easily during the seminar, but certainly I want to answer questions. But even after the seminar, if you find anything that is of interest, if you're interested in getting our code or anything like that, or the models, more information, don't hesitate to talk to me. With that, this is a work in progress. A little bit of I'm going to tell some old stories that some of you may have heard before, but there may also be something that we are trying in terms of machine learning. I will tell you what the big picture that we are interested in. First and foremost, in terms of multi-phase flow, which is itself is a big area, I'm interested in dispersed multi-phase flow because that's the one that I've been working on. And this video that you see from NETL is absolutely fabulous video because it really gets to the core where you can see by zooming in, you can see individual particles, which I call microscale, and you can zoom out and you can see instabilities, and then you can go to the full system. But on the other hand, the other picture shows some gigantic scales on which multi-phase flow happens. And these are the problems that all of us are interested in. And we also know that there are sort of like 4 tools people have used. Particle resolved simulations is great because you don't need to make a whole lot of assumptions in there. I won't say that it is completely assumption free. There are some modeling involved, but they are many a time so well grounded that you can take those governing equations as God-given and you can compute them. But the downside, of course, as you know, it's limited. You can't do a full riser or a full mixing tank with that. Euler-Lagrange has become a workhorse in certain circles. Again, it involves modeling. Mainly the modeling is that the fluid phase invariably is average because you don't look at the fluid on the scale of the particle because you treat the particles as points, so as to speak. The advantage is that you can go up to billions or even tens of billions of particles and track them and let them collide and do whatnot. But for a very practical approach, you want to simulate the entire volcano or a sediment migration in a river, etc. You have to resort to some sort of a fluid kind of model. Here you average both, both phases are average, so more approximations involved. The crux of my talk is that the science question is, yes, we are limited to sort of Euler-Euler simulations of practical systems. How can we make them behave as accurate as particle resolved simulations? How can we upscale modeling information in a systematic way and make use of modern developments and make Euler-Euler as accurate as you can? So that's the essential theme. So this problem shows, this is say a riverbed looking from top, and all 3 approaches are being deployed in this game. The very top one is some very early videos from Marcus Ullmann's group. He has much better, much bigger systems. But you can get the idea that here you have to put about 20 grid points at least per particle. But you can faithfully simulate how the river flow is sort of moving the particle from left to right. If you go down in the middle frame, you have Euler-Lagrange point particles. You let them collide. And the most important thing is that you can now start looking at instabilities. But of course, there is modeling involved, and you can see these ripples forming naturally over a physical times of the order of, say, seconds. And their distances are of the order of, say, several, maybe a centimeter or maybe more. At the bottom, the same problem simulated with Euler-Euler. Of course, you can make the system even bigger, where you can see how the ripples interact. And that's exactly what we did, ripple interactions we studied. But then you can even coarse grain it and you can see a kilometer. Of course, then you will stop seeing ripples, but you may start seeing dunes and things like that. So this is the thing. So again, the question is that how can this Euler-Euler simulation embed all the wonderful physics that are there at the lower scales? Now, to do that, let me just focus on Euler-Lagrange, and I want to say, how can one make Euler-Lagrange behave like a particle resolved simulation? Here is just a very high-level equation that one writes, say, for Euler-Lagrange. So you have to track fluid quantities, say, on some grid, and you have to track particles, say, millions or billions of them. And there are terms in these equations that needs to be modeled. Because you're averaging the fluid, you have a Reynolds stresses, a closure problem. And in addition, these particles are not resolved, or bubbles or droplets are not resolved. Therefore, you have to come up with drag, lift, torque, heat transfer, mass transfer models. And this is where these two boxes are the red circle terms are the ones. If you make them very good, this simulation could be as good as DNS in some ways. Okay, so that a lot of emphasis is on this modeling. Today, I want to only focus on drag and lift forces, but the idea permeates, and you can do the same thing for heat mass transfer. And also, we have done Reynolds stress modeling. So a very systematic upscaling of information. Okay. Now, we can go to Euler-Euler equations. Then this I is wrong, I'm sorry. So we're not tracking particles anymore. So you have fields of representation for the particulates also. So you now have particles phase averaging as well. So you have Reynolds stresses both in the gas phase or fluid phase and the particle phase. And you need to model them. So I want to make some observation, which I've already mentioned. These Euler-Lagrange and the Euler-Euler, which I will represent as EL and E, if you use perfect models, they're almost as good as PRDNS. I say almost that because you are losing some degrees of freedom. So there's no free lunch. You can't get them back. But the question is, those modes, those degrees of freedom that you compute can be as good as possible. Okay, that is the goal that we have. Okay, so we want to approach perfect models. The other thing is that Euler-Lagrange simulation is about can be a million times coarser than PRDNS. The numbers are very simple. Instead of having 20 grid points per particle, you can have hundreds of particles within one grid cell. Okay, so there is a good bit of saving in each direction, and as a result, your overall saving can be, in fact, it can be even bigger than a million times. You can have hundreds of millions of degrees of freedom reduction. Okay, that's significant. But the onus, the responsibility is that subgrid models must be as good as possible. Now, if you go to Euler, you can have further savings. And today, I will focus on going mostly from particle resolved to Euler-Lagrange. And the same ideas can, not going to talk a whole lot about it, ideas can be extended to do Euler-Euler as well. Okay. In essence, another way to look at this is super resolution. So in other words, if you do an Euler-Lagrange simulation or an Euler-Euler simulation, can you predict all the small details that are going to happen inside that you have not computed, but take those details into account in advancing your state? So that's the crux. In other words, can you aim for super resolution within your simulation? Okay, so the same thing I'm going to bore you to death is that our force modeling quest is that in an Euler-Euler force model, you're going to have a bunch of input. You have particles position, you have your neighboring particles position, you have your gas flow within your cell. With that, you want to predict forces and torque, and you want them to be as good as possible. And the same kind of stuff for Euler-Euler as well, where you don't have individual particles, but you have volume fraction, you have average velocity of. So how can you make these models as good as you possibly? Okay, so I'm also, you can look at it two different ways. In Euler-Lagrange, in particular, you can look at it, this prediction of forces on particles at two different levels. You can think of like, hey, I want a deterministic model. One important thing about Euler-Lagrange is if you're tracking all the particles know where all the other particles are. You can make use of it. And you can construct the subgrid information that you have not calculated. And therefore, you can deterministically calculate the forces on particles, hopefully very accurately. That's a deterministic approach. A little more expensive, but not advocating that that's what everybody should be doing, but that's a framework one can use to get DNS-like results. Then you can average, you can construct stochastic models out of it. And of course, in case of Euler simulations, you don't know the individual particles, so the models are invariably stochastic in nature. In other words, there will be fluctuations, there will be uncertainties. So a good model is one which not only tries to mimic the particle resolved simulation, but also carry along with some uncertainty information. Okay, so those are the sort of requirements. So in terms of modeling frameworks, I have thrown at you a number of different things. I've said that we can have deterministic. If you look at deterministic model, I'm going to talk about two different things. So one of the deterministic hallmark of a deterministic model is that it accounts for your neighbors. So it's a higher class of information where each particle doesn't ask the question, what's my surrounding flow? And then I will give you the drag, okay? It will say, what's the surrounding flow and at the macro scale, but where are my neighbors? Because I could be in the wake of another neighbor. So I have to adjust my drag. That kind of a concept is the deterministic model. And within that, you can ask one neighbor at a time or n neighbors at a time. It's a truly n-body problem. So when you throw a million particles, it's a system, it's an n-body system, okay? And it's very complicated physics problem, but we're trying to find ways to nibble at it and make advances. Okay. The other thing is that this is one of the key themes that I will talk about in terms of machine learning is that often it is hard to predict just force, because ultimately we want only the force on these particles, but force is kind of hard. And in machine learning, people know that maybe there are some latent variables, some inherent hidden variables. It's easy to get them first, and then you can go to the final answer that you want. So it turns out that it's better and easier to predict the flow. And then from the flow, of course, you can integrate the shear stress around the body, etc., and you can get the force. And therefore, from a machine learning perspective, that one of the take-home message, if you have for machine learning, is that don't only try to predict the final answer, but think about what is predictable, what you can train easily. Okay. And of course, once you have the deterministic models, Again, this is not the end in itself. Really, for practical things, you may need a statistical model, but how to get the statistics accurately, you may want to have a way station of a deterministic model, which will give you DNS-like data for billions of particles. Then you can average it to create the appropriate statistical models. All right, so that's the lengthy introduction. So what am I going to do in the rest of the talk? First, I want to talk about neighbors matter, okay? The random nature of particle. What makes multiphase flow exciting is that it's stochastic in nature, mainly because of turbulence, also because the particles are random, okay? There is a randomness associated with it. Then I'm going to talk about flow prediction, which is I'm saying there's sort of a latent variable that can be used to do the force prediction. I will talk about pairwise approximation first, then I will talk about the real deep learning that we have been using for n-body prediction. So in all these things, the training data must come from PRDNS. And then we use machine learning and multiphase flow understanding to come up with machine learning model. Then once we have a Euler-Lagrange that behaves as good as PRDNS, particle result will be replaced by Euler-Lagrange as training data. And you repeat the process and you get an outstanding Euler-Euler model. So that's the bootstrapping strategy that we're going to pursue. So let me get to the first point, which is neighbors play a big role. Okay, so here is an Euler-Lagrange simulation. So let's say a big tank. Let's say the particles are going from left to right. Let's say this is one cell, one big cell, let's say, finite volume cell. And that this cell has hundreds of particles. And there's a random distribution of particles inside it with an average volume fraction of 11% and a Reynolds number of about 16. Now, if you ask, do we have a good model to calculate the average drag for all these particles, given the fact that there are 11% volume fraction of particles and the average Reynolds number is 16? The answer is yes. There are 10-at-least correlation and a number of other really good correlations are there, which are functions of this Reynolds number and volume fraction, and you can find the average drag. That drag, average drag, is plotted as the red line. Now, if I go and ask a different question, I do a particle result simulation, and I get the drag force on all the individual particles, and I plot them. Say, in this case, I have about 450 particles. This data is for a slightly higher volume fraction. You ask, what's the force on these particles? Some of them are very large, and they are given in red, and some of them are very low, as you can see here. Some could be half the average value, some could be twice the average value. Why so? The answer, so there's a big scatter, and the question is, if we want a DNS like Euler-Lagrange, you better capture some aspects of the scatter. Okay, you just can't satisfy with the red line. Okay, that's the key. How do we systematically build a machinery that is not just stochastic, but even deterministic, so that it can come as close to this as possible? So that's the question. Before that, why do some particles have higher drag and others? It's pretty easy. In this particular two scenarios, I'm zooming in on two particles named A and B. The flow in this case is coming into the board. It's quite obvious that A going to have a low drag because it's being shielded by two guys upstream, whereas the two guys in case of B are upstream, but a little bit too off, so they're channeling the flow. So B's drag is the 80% more versus A's drag is 50% less. So if you look at the scattering, by the way, the prediction of why the drag is high and low is nothing but easy. You cannot ascribe it to a local volume fraction. It very much depends on the anisotropic distribution of neighbors. Okay, neighbors are important. And interestingly, they also follow this scatter of data, both the drag force and also their side force. Even though the flow is into the board, each particle is going to feel substantial side forces, okay? So these are sort of Gaussian sort of distributions. So Jesse and others are working on stochastic model, which is a very good approach. But the data must come from these kind of simulations as to what's the level of dispersion. But one of the effect of stochastic model, if you assign randomly forces to these particles, you may give B a very low drag, and you may end up giving A a very high drag. That's a risk in a stochastic model. So deterministic model will try to preserve as close to DNS as possible, but of course it's expensive, may not be scalable. But the question is, can we use deterministic model to even train and obtain more robust stochastic models? Okay. So again, this point is that what we have been doing is the best available model is that if you take a volume, in this case only 10 particles are there, you can find what the drag is based on local volume fraction and Reynolds number. But how do we go to the next step? How do we assign improved model for the cyan colored particle? You got to account for every neighbor and take its account into modifying the drag of this particle. So it's sort of like molecular dynamics. So there's a hydrodynamic force due to average flow, but can we also build in neighbors' influence? Okay, so that's a very simple thought. And if you're going to do molecular dynamics, why can't we do this one neighbor at a time? But that's not how hydrodynamics is. Hydrodynamics, of course, is nonlinear, and it must be treated as an n-body problem, okay? So what we said is, first, let me do an approximation and do a pairwise interaction, and every neighbor's influence will be measured in terms of a change in the drag and the lift force of the particle. That I will talk about how to build these neighbor influence maps. But then, if we want to take all the neighbors into account simultaneously, then you got to go for some machine learning. And that's the idea that I will talk about in the last about 5, 6 slides, or maybe 10 slides of my talk. Okay. Again, very simple. This idea of pairwise interaction is nothing new. Statistical physics has been doing it for centuries. Therefore, we want to borrow a lot of ideas from statistical physics. Again, I already mentioned that it's being done in molecular dynamics, neighbor at a time, in astrodynamics, one pair interaction, etc. So we want to do the same thing very well, understanding that that's only approximation in our hydrodynamics problem. Hydrodynamics problem is very complicated, unfortunately. Okay. So the idea is we want to create these pair interaction maps. Pair interaction maps implicitly are dependent on these 4 variables. So if you have a particle and say going to influence all the neighbors around it, that influence depends on the flow. So this particle has a flow coming from the left to the right. So this influence is inherently axisymmetric. So where the neighbor is going to be measured in terms of radial and angular distance. And the 2 other parameters are, hey, what's the Reynolds number of the local flow and what's the volume fraction. So if I create these maps, then I can take care of every neighbor's influence. So the force on any particle will be sort of a mean force times its drag plus influence of all the neighbors. So a very simple idea. So how do you create these maps is now the detailed question, and that's done with very simple machine learning technique. So what we do is very simple. We take a lot of DNS data. This picture is incorrect for this case because this is the same idea we use when we use machine learning in the n-body problem also. But I'm going to do a pairwise interaction first, try to understand, hey, how can I construct the flow? And then once I construct the flow, then I can predict the force. Why flow prediction easy and force prediction is hard? If I look at the particle resolved data, I have perhaps 10,000 particles whose force I have from DNS, whereas I have the flow given on 100 million grid points. This is a lot more data for flow, and therefore I can constrain it and I can build a better model for predicting the flow. Once I have the flow, I can calculate shear stress and pressure distribution, and I can calculate the force. So this two-step process, this flow is a latent state in case of machine learning to reach the final goal. So flow prediction is very important. So how do I do from the PIEP model perspective? I won't get into the details for any of them, sort of a little high-level talk to give just a concept. So we take a PRDNS data, different volume fraction, different Reynolds numbers, and then I ask a very simple question. There exists a wake, axisymmetric wake of every particle for this Reynolds number, for this volume fraction. If I take that wake and I patch it on all these particles and I sum it up, it should recreate the particle resolved DNS data accurately. Find that flow. And that's exactly what machine learning does. It goes and finds what we call a superposable wake. In other words, this is the wake of an individual particle at a finite Reynolds number, at a finite volume fraction, that when I superpose for all the particles will look like DNS data as close as possible. So that superposition is given here. So of course there is an approximation. It's not treated as an n-body. In an n-body problem, we ask the same question. Hey, I have all these n particles. Find me the best flow that will approximate the DNS data. But in a pairwise approximation, we use this superposable wake approximation. Now, here is the result. So this is the actual data computed with 35 million grid points. It's a 3D box, but I'm showing only one slice. And here there is no CFD. I take these superposable wakes and I just put it on every particle and I add it up. And our square value is about 80%. So it's not perfect. The glass is not full, but glass is about 80% full. This is better than anything else, whatever we have. So the question is, what can we do with this information? This is basically creating subgrid information, knowing only the particle position and the mean flow, filling in all the details without doing simulation. So this is exactly what I was set out for. So we are able to do it at sort of 80% accuracy. So we did that for different Reynolds number, different volume fractions, and here are the superposable wakes. I first want to tell you that there is a lot of physics out there. This data wasn't available right there. So you can't get this by just statistical simple averages. So you need a little bit of inverse problem to get it. Okay, so you can call it machine learning or you can call it regression. Somehow something has to be done to get these things. Now look at these wakes for a high volume fraction. I first thought that they ought to be very complicated. It turns out just the opposite. When there are many, many particles close to each other, they clobber each other's wake. And I'm getting back a front-back symmetry, much more than at zero volume fraction. Now, when you think about it, this physics is very interesting and becomes sort of obvious. Yeah, the wakes get simpler when you have many more particles, okay? So machine learning has a lot of physics to give as well. Another very interesting thing is the so-called this concept. So if I'm showing you flow prediction, but then how do we go to force prediction? Well, we have a very simple theorem, Maxi-Rayleigh kind of equation. So to calculate the force on this, say, the ith particle, what do I need? I need the undisturbed flow at the particle. What's the undisturbed flow? Well, pretend that this particle doesn't exist. What would be the flow due to everybody else? Now, if you want to just get at it using particle resolved simulation, it is impossible because you want to know the undisturbed flow of this. You got to do a DNS without that particle. You want to know the undisturbed flow of this particle, you got to repeat another DNS without that particle. But with superposable wake, I can just superpose without this particle and I get undisturbed flow quite easily. So in other words, conceptually, the superposable wake is a cool idea. It's able to get undisturbed flow of any particle. And once I know the undisturbed flow of any particle, doing a surface average of this undisturbed flow and volume averages of pressure and velocity. There's a lot of details in there, and I don't want to get at it. The important thing is that if you know the undisturbed flow, you can get the quasi-steady force, Archimedes force, or a pressure gradient force. Every force on this particle can be precisely obtained from that undisturbed flow. And this is how we get from flow to force, very grounded in very solid theory. Okay, so what we do is that we don't do it the way I said. We calculate each neighbor's influence as a force. So they are calculated as a drag map, lift map, and a torque map. What this is if I have a black colored particle, what does this black particle does to another particle which is somewhere around it? And the second particle, obviously of the same size, its center cannot be within this white region. So I don't need that information. The center of the second particle can only be outside, anywhere outside. Suppose if it's here, I can read off from this map and I can say, yeah, this black colored particle is going to create a negative drag on this second particle. It's going to create not so much of a lift force, maybe a little bit of a torque. So in other words, neighbor's influence has been encoded as very simple maps. And these maps are functions of R and theta. They are axisymmetric, and they are functions of Reynolds number and volume fraction. I create these maps and I store them and I consult them in Euler-Lagrange, and I keep moving the particle. So the idea is very simple. So from flow prediction, we can go to force prediction and then use it for moving particles. So with that, I have, let me look at about 10 minutes, okay? And I have to cover about 12 slides. I will do my best. So from now on, I'm just going to show this framework, how good it is, okay? What does it do? So here I am showing a simple PR, particle resolved DNS data for a few hundred particles. This is now this is testing data. I have used it to create the model. So the test data is different from the training data. And that DNS data of drag is plotted. Different particles have different forces. This is what we currently do, the best model. It does a great job in predicting the average, but it's unable to predict particle-to-particle variation in drag. So all the particles will get the same average force. Okay, this is what current finite different, Euler-Lagrange and Euler-Euler methods do. And my preaching is we can and we should do something better. And of course, the perfect model would be the 45-degree line. If you have a model which can do as good as this solid line, then your Euler-Lagrange is perfect. And that's exactly what I was talking about. Now, our PIEP model doesn't do a perfect job, but you can see it does up to 75% accurate job. Okay, so that's pretty good. And I'm not going to show you, but for the lateral force also, we can predict it with great authority. Now, let me show a couple of old slides. These are about 3, 4, 5 years old. I've shown it many times. But for the benefit of students who haven't seen it, let me show it. So here's the very simplest example. 2 particles falling down. Here is the DNS. Very easy to do. Here is the classical model. No DNS. Just the 2 particles are moving. But each particle doesn't know the other exists. And they obviously will fall together. Now, this is the PIEP model. No DNS. Each particle understands the wake of the neighbor, consults the force map, drag, lift, and torque, and they move and rotate according to those drives. And you can see the drafting, kissing, and tumbling is fairly well captured. Now, in the interest of time, let me move and let me show you can easily go from 2 to 80 particles. DNS maybe takes 10 hours on 32 cores. Here it takes seconds, or in a MATLAB code, you just track position, velocity, even rotational velocity of these particles, and you track them. Now, clearly, this problem is chaotic. Therefore, the exact locations are not the same, but the statistics extracted from the PIEP model without any CFD is able to do a great job. So the idea is that now we have a model that brings in subgrid information in a reasonable way. So here is a scaling up to 1 million particles. Here is the same system that I showed at the very first slide. Really, these particles are falling down, settling down. This is an Euler-Lagrange simulation, and it involves 3.5 million grid points and about 2.5 million particles. This is what the actual flow looks like. The Euler-Lagrange simulation is average. It doesn't capture the wake of every particle. But these particles are moved according to the PIEP model. In other words, every particle here in the simulation knows where the neighbors are and uses that information to create what perturbation is introduced by the neighbor. Therefore, if I were to go and say, hey, what would have been the locally resolved flow? Such a flow would look like this. This is not the flow we compute, because we cannot compute it, because it would require 226 billion grid points. But the point is, the particle motion in this flow is as good as if we had done a simulation of 226. The fact that this flow doesn't have this detail is a loss of information you cannot easily recover. But the point is that the subgrid information is incorporated in this simulation. Now we have measured collision rates and lots of things with this. Now you can say this Euler-Lagrange simulation is as close to PRDNS would require, say, hundreds of billions of grid points. Now I can use this information to construct models, even models for Euler-Euler. And that's the plan that we have been pursuing. And that's exactly what I've done. So what we have done is that we use these models that have been constructed with PIEP models to create Euler-Euler models, okay? And I don't have time and I don't need to do that. I'm going to quickly move. So the main point is that if we build an Euler-Lagrange model, which we can have a better faith, then we can use that to bootstrap and create drag forces for varying Reynolds number, varying volume fraction, varying particle motions, etc., and create models that can be used in Euler-Euler simulation. So I'm going to skip this slide, and I'm going to sort of quickly recap this PIEP approach. Is that we first did flow prediction, and we used the flow prediction to force prediction. And we are able to do now Euler-Lagrange simulations with improved prediction, which behaves closer to fully resolved simulation and can be used to generate a lot of data for statistics. Okay, that's a sort of a summary. Now, I want to take another 5 minutes to tell you how we go and do n-body problem. Okay, so what I'm going to do is that the training data for me is that I'm going to data mine. I'm going to go take my PRDNS, put a box around every particle, and I'm going to show to the training, to the deep learning, I'm going to show, hey, what's the flow around this particle and where the neighbors are. I'm going to show a box of, say, 5 diameter by 5 diameter, 5 diameters. So if I have 10,000 particles, so basically I have 10,000 little boxes of information that I use for training. And the idea that we are going to use is called generative adversarial network. Why? You know, this has revolutionized many different fields, including cosmology. One thing is that, say, for example, if you show an outline of a bag and give many training data, it can fill in and tell you what the bag looks like. You give an outline of any kind, a road, it fills in the data. So our idea is very simple. Hey, I'm just going to tell you where the particle neighbors are. You fill in and draw the picture for me. Get this kind of a flow. Think of it like a filling in this picture. Think of this as a Van Gogh and draw for me this flow, and I want to measure how good it is. So the generative adversarial network is good. Now we're going to do a conditional or a constraint. So we're going to impose a lot of physics on it. It better be incompressible, let the flow be satisfied, no slip, and so on and so forth. So the idea of a generative GAN is, for those who don't know, it's very simple. There is a network, a neural network generator, and another neural network, which is a discriminator. A generator, given just the particles, it will create a flow, synthetic flow, which we want it to behave like a particle resolved simulation. So you send this synthetic flow and the ground truth, and the discriminator tries to tell which is true and which is wrong. The discriminator initially is very good. It will easily tell the synthetic flow is flawed, and the generator will try to get better and better, and they reach an equilibrium. Eventually, the generator gets so good, it creates flows that will fool the discriminator. Okay, that's a very simple idea. And then once you have this flow within a 5 by 5 by 5 box, we can use another network to improve, because for force on this red particle, I don't need the big flow. I just need a flow in the immediate neighborhood. So there's something called attention mechanism which can be used to really fine-tune, get high resolution data around this particle. Okay, so that's what we do. And I already told you that we use symmetries. We have worked a lot on how to build physics into this machine learning process, conservation of mass, no slip condition. So these are details. I'm more than happy to talk with anyone who is interested. In the last few slides, I want to get to the final results. So here is the particle resolved data. This is just a volume rendering of, say, velocity. Here is the n-body prediction of the flow in this sort of a little volume. This is particular case, volume fraction is 21%. Reynolds number is about 16.5. We used about 3,800 sort of like centered particles and volume around it, and we use a validation of 546, and then we did training testing on several hundred samples, and they are distinctly different. So nobody can blame us that we use the same data for training and testing. So this is the strategy, and here's a picture. This is the actual flow. Took hundreds of hours on a 500 processor. This is a GAN prediction. This is the prediction. You can look at it. The error is really very small. So the training is able to predict it really well. Here is the velocity vector field. Again, it's able to predict it fairly well. In terms of number, two different cases, basically two different Reynolds number volume fractions. What I'm plotting here is R-square values, and the R-square values are pretty high, so the prediction is pretty good. Here's the same data. Here I'm taking just a slice, and it's going through the box. The DNS data, the n-body GAN prediction. The important difference is that it took 500 hours. I said something wrong. It's not 512 cores. On 8 CPUs, it took about 500 hours. We have done it on 512 nodes, then it obviously takes much fewer hours. In terms of GAN, training takes about 24 hours on 4 GPUs. But once you train, I can generate the same synthetic data in half a second. Okay, and that's why I'm saying once we train it, I can repeat boxes, tens of thousands of boxes, or even million boxes. And I have plenty of data for averaging. And this is the strategy. This is how the Euler-Euler models that I skipped over were generated. And how good it is, how accurate it is. Well, in this particular case, R-squared value of the n-body problem. The PIEP model, the pairwise interaction itself was good. It was able to get about 80%. Now, the n-body GAN, and with attention, we're able to get 97% accuracy. So in other words, we can get the force on this particle without DNS, just with training data to 90+% accuracy. Okay. So I want to stop there, and I want to just say a few words on summary, and then open for questions. One of the things is that the main message I really want to say is that there is we are on a threshold of some revolution. We can revolutionize the modeling of Euler-Lagrange and Euler-Euler by incorporating more information on many experiments and simulations. We have not been really using the full potentials of our DNS, and we have an opportunity to upscale. Ours is just one method. I mean, there are many other methods. The other thing is that machine and deep learning, they have built such incredible machinery, which we can embrace and benefit from. And what we have been doing is that we are extending these deep learning approaches to other related problems and try to do more along the lines that what we have been doing. Now, let me stop there. Omar, I can take questions if people have. I'm sorry, it's a bit of a rush.
No, it was really great. Thanks very much, Bala. Fantastic. Let me start with a couple of questions because I don't see any in the chat, but certainly people can come in. Yeah, obviously, I think what you presented is really quite rational. It looks really quite powerful. One thing I was wondering about is about the nature of the particles. Obviously, these are non-deformable particles. And so the natural question arises, what happens if these particles are deformable and where they can undergo, coalescence, breakup? What if the flow surrounding these particles is, quite complex in itself? But maybe just tell us a little bit about how it's extensible, this methodology is to deformable particles.
Omar, great question. I am selling not just what we have done in the case of rigid stationary particle. By the way, the training is for stationary, but we can apply this, and we have tested this, as I showed, for moving particles. Okay, so but the approach and the framework is, how do we do droplet or deforming particle resolved simulations? Yeah. And you get a lot of data. How do you construct a framework that can make use of that data and reduce it into some physics-inspired models such as pairwise interaction and its extension into pure machine learning kind of tools that would be able to recreate the missing information that you will not have in a coarse-grained simulation? That floor plan transcends the particular nature of the problem that we are presenting. I cannot see why one cannot do this for a deformable particle if you provide the right kind of information. So in other words, you must be able to predict to a certain level of accuracy how a droplet will deform at the next instant. Yeah. Put deformation as one of the predictive outcomes of the problem. Yeah. Okay. So one of the things that I did not mention is a good understanding of physics is of absolute essence in constructing meaningful models that are robust and just not overfitting, curve-fitting exercises. Okay.
Yeah.
But I think there is a greater opportunity.
Yeah, absolutely. I guess I was just thinking that at some point, if these particles are deformable, then their numbers could change because of coalescence or breakup or whatever. But it sounds like it is potentially possible to try to get that kind of subgrid scale information. It may be a bit more complicated than just communication through wakes, though, right?
So you put this in a machinery, given your droplets positions. So what do? You have a bunch of droplets positions, and you want to know what happens to them at a little time later. You have the option of either doing fully resolved simulations, which you need to do to get the ground truth, or experiments with the ground truth. Then you say, I don't have the luxury of resolution, but is there a machinery by looking at these droplets' current position and maybe past history, tell me what the microscale physics should be. Then you use the same machinery as you used to do, and then break them, coalesce them, do whatever you want. And that microscale missing information must be predicted in some efficient way by the system.
Yeah, sure.
Okay, so that's the idea.
Great, thanks. Thank you, Bala. There's a question from Claire in the chat, and it says, asking whether you tried different types of GANs, or did we just go with one type only? So I'm just wondering what the answer to that question was.
Claire, very good question. Our problem, the training, in my hurry, I did not really emphasize, the training was done with static data, but the deployment was with freely moving particle. So again, this is where our understanding of physics comes in very handy, is that we really didn't have to do a tempo GAN or something like that to do time-dependent prediction. Time dependence came in through our outer shell, but the model development was done in a static environment. Therefore, we used a very simple physically constrained GAN that we just constructed ourselves using PyTorch. Okay, and I'll be more than happy to share some papers with you. We did not try many other GANs because I don't know what more could we do beyond 90% accuracy, because we are not computer scientists. We just use them. If others are interested, we're more than happy to share. And we're touching the tip of the iceberg. There is so much that can be done.
Yeah.
I hope I answered your question, Claire.
Okay, Claire. Yeah, thank you. Thanks, Claire. Rosella is asking a question. It's wondering if you've implemented any kind of cleaning or reduction or compression of your data before training.
No, we just curate the data. Okay, you have to. I mean, depending on the problem, we have to curate the data. Our DNS, say, is done on, say, just I'm going to throw some numbers, say 500 million by 500 million by half. No, I'm sorry. So if it has, say, 500 million grid points, or we have a box of very 10 particle diameter by 10 particle diameter, you can't give that data to any existing GPU. It just doesn't have the memory, nor is it necessary. So what we do is that we curate the data. We make each particle within the PRDNS as the reference particle or the center particle. So we sort of shift the box around each particle, and we pull out the data around each particle. This way, that particle's neighbors are shown, and you use that data for training. I hope I answered the question. So it's more of a curation, but you know, we may use one grid, we may train the data on a slightly different grid, so interpolation, etc., may be necessary. But those are nitty-gritty details. I don't think the outcome greatly depends on that. Okay.
Yeah, I share your feeling. I think the results that you put up look pretty robust to me, for sure. One more question, if it's okay, Bala. It's from Gabriel, and he's wondering, if we start to put in additional complexity, say, I don't know, polydispersity or deformability, he's just wondering whether suddenly the dimensionality of the problem makes it intractable. Any comments on that?
Gabriel, great question again. You know, the PIEP model or the night model, when you look at it, let's look at the night model, or what the N body, the GAN is, what is it trying to do ultimately? Okay, so I said that it takes in static data, and what are we trying to ultimately predict is that force on a particle, and it has, let's say, dozen neighbors. So what goes into the training, in a sense, is the location, the relative location of the dozen neighbors, maybe the velocity of the dozen neighbors, maybe the rotational velocity of the dozen neighbors, maybe the acceleration of the dozen neighbors. So we're talking about position, translational velocity, translational acceleration, rotational velocity, rotational acceleration. So you can see for the dozen neighbors, you have vectorial quantities. So there itself, you have 60 information along with Reynolds number of the flow, volume fraction. You can think of already there is an incredible curse of dimensionality at work. And we are asking the neural network to say, go take this 60-dimensional space, find me the solution. And that's what it does. Now, what prevents you to add my neighbor's shape and how the shape is changing? You don't even have to parameterize. If you use GAN, your neighbor is looking like an ellipsoid, you just send that information. So I don't see any stoppage. And this is precisely where neural networks have really championed is, this is not a problem that you can say, I want to build a 60-dimensional model. So on the other hand, it's all statistical process. It does a reasonably good job in extracting those patterns that we are unable to extract ourselves in a naive way. Okay.
Thanks a lot for that. That's great. Maybe we take one more question. There's a good question here from Rashid, which is, I think, about the coupling between the particles and the flow in situations like, for example, cavitation, you know, where you can have, you know, a strong coupling back from the particles onto the flow. So what happens in situations like this?
By the way, Rashid, the simulations I showed, these falling particles, it is a two-way coupled simulation. Okay, in fact, the flow is driven by the falling particles. Okay, I don't see two-way coupling. See, two-way coupling simply says I feed the force that is exerted on the particle by the flow back to the flow. The better job I do in calculating the force on the particle, the better the job that I do on the feedback force. Of course, in Euler-Lagrange, there is another layer of approximation. How do I feed the force back? So there are approximations. So I'm not here to say that when you do an Euler-Lagrange simulation, it will be as good as particle resolved simulation. The question is, yes, when I do an Euler-Lagrange simulation, I save it 1,000,000 times or 10 million times. There is a price to be paid. But the question that is being asked is, how best an Euler-Lagrange simulation can I do? Or similarly, when you do an Euler-Euler simulation, hey, given a grid of million grid points, I am constrained. What is the best Euler-Euler simulation can I do? And I claim currently we are not doing the best job we can. And we have an opportunity to, all the younger people have the opportunity to build better models and upscale the information and really revolutionize the way we do Euler-Lagrange and Euler-Euler simulations.
Fantastic. I think this is a great note to end on. Bala, thank you so much for being our inaugural speaker. I don't think we could have hoped for a better speaker than you. And what you talked about here is right in the middle of the agenda of Premier. So it's super relevant, really, really relevant. And yeah,
Emilio has asked a question about papers. For
Yes.
anybody, I just want to say, papers, of course, you can search on with my name in Google Scholars. You could throw away paper that you don't want, maybe look for last 5 years and look at things like machine learning and things like that, and you can dig your way through. But the main thing is that I'm more than happy to put you in touch with my students and other people. And the whole idea about this is to spread the message, get other people excited, and you guys can do even more discovery, way more than our group has been able to do.
Yeah, thanks for that. I was hoping you'd say that because, I mean, Emilio, we can provide some links, so Noshin and I could do that. Don't worry about that. But if we can have a collaboration with you, where, you know, hopefully in the fullness of time we can host people, or at least start to do this online, so that eventually when things go back to normal, we can actually host you and group members, etc. I think that would be really brilliant for us.
Absolutely, and the PIEP model details, machine learning details, anything, and even sit with you guys and brainstorm about how to incorporate evaporation, cavitation, or deformation. These are the areas we need to go, because I know that you guys are doing a fully resolved simulation, so how to get more out of it, okay?
Yeah, that'd be brilliant. Thanks so much, Bala. Thank you for everything.
Thank you all for wonderful questions. Thank you. I really enjoyed this engagement. Thank you very much.
Thanks, everybody. Bye.